Okay, welcome. This time we are looking at finding the area beneath the graph of y equals the square root of x over the interval 0 to 1. Okay, for this problem here, we want to do it by setting up a sum. So if you already know the other way to do this problem in calculus, we're not doing it that way. Okay. As you try to do this by setting up a sum, you quickly discover that you got a bit of a problem. See, because to evaluate this, we eventually got to evaluate f of xi. And that's going to involve doing a square root of some expression involving I. That's going to lead to sums involving square roots, and we quite frankly just say yuck. So since we don't want to do that, we approach this a different way. And it's kind of a creative way of doing it. It's probably not something you may notice or figure out right off the bat, but because that square root, we have a problem. So we proceed by taking care of that problem first. And we do that by saying, okay, let xi be I squared over n squared. Because you see now, when we later on do the square root of that, the square root goes away. And because I and n are both positive numbers, it's going to result in just being I over n. Now, since we've started by defining xi first instead of delta x, we have to figure out delta x. Now, delta x is the size of each interval. Except it's not delta x now, it's delta xi. It's delta xi. Because it's going to change from interval to interval. So it's the difference between the right and left endpoints. And so we can use xi now to figure that out. I squared over n squared minus I minus 1 squared over n squared. And then we expand that out and multiply everything out and simplify. You may want to, again, at different points in this video, if you want to slow it down and work that out yourself, please pause the video. And as we simplify now, we get that delta xi is 2i minus 1 over n. So now we know xi and we know delta xi. It's different. It depends on I. Now before we continue and actually set up our sum, let's just consider a little bit about what this is doing. If we consider it for n equals 4, when n is equal to 0, or I is equal to 0, we would have to get 0 over 16, which is 0. And then we continue for I equals 1. When I is equal to 1, your next point would be, in the partition, would be 1 squared over 4 squared, would be 1/16. And then we move on to 2 squared over 4 squared, would be 1/4. 3 would be 3 squared over 4 squared, would be 9/16. And then finally, I equals 4, would be 4 squared over 4 squared, would be 1. And so you can see how the intervals get progressively bigger as we go from left to right. Okay, so that's a little bit of a picture, and again you can see the widths of each of those intervals is different, and that's given by 2i minus 1 over n squared. Okay, so now we're ready to begin the problem. We start by setting up the sum. Sum is f of xi times delta xi. That's the height, f of xi, times the width, delta xi. And then we plug in what those are. So f of xi would be the square root of I squared over n squared. And then minus 2i, times 2i, not minus, but times 2i minus 1 over n squared. Okay, we simplify. Square root of I squared over n squared is again just going to be I over n. And then if we distribute that and break things up, we'll get the sum of 2i squared over n cubed, multiplying the first term, minus I over n cubed. Okay, and then at this point now, we can factor out the 2 over n cubed out of that first term, and have that times the sum of the I squareds, and then minus, and then we have 1 over n cubed that can be pulled out as a common factor, times the sum of the i's. Okay. And so at this point now, we're ready to use our sum properties, what we know about the sum of the I squareds and the sum of the i's, to work the problem out. Okay, so moving on. At this point now, I've just rewritten what we have here to work out. And so we invoke the formula for the sum of the I squareds. And so we get that it's going to be 2 over n cubed times n plus 1 times 2n plus 1 all over 6. And then we invoke the formula for the sum of the i's. So it would be minus 1 over n cubed times n plus 1 over 2. Okay, at this point we can do a bit of simplifying. We can cancel out the 2 and the 6. We can cancel out the n and the n cubed. Okay. And then in the other one there, we can cancel out the n and the n cubed. And that's all we can cancel out. Okay. Now, I'm going to go ahead and do a bunch of simplifying to save us a little bit of time. You may want to pause the video and kind of work this out on your own. But as we simplify now, after a couple steps of simplifying, we will have 2n squared over 3n squared plus 3n over 3n squared plus 1 over 3n squared. That's from the first part. And then the second part, because it's minus, we'll have n over 2n squared and minus 1 over 2n squared. Okay, and then we continue on. There's a little bit of simplifying that we can do here. So 2n squared over 3n squared is 2/3. Then we'll have 3n over 3n squared is 1 over n. And then 1 over 3n squared. N over 2n squared is just 1 over 2n. And then minus 1 over 2n squared. Okay, now we're almost there. Now we're almost there. At this point, we can now say, hey, we're going to eventually take a limit. So all those things that have n in the denominator, as n goes to infinity, are going to be 0. That leaves us then with one number, 2/3. So the limit of our Riemann sum, because it does exist, that is the area beneath that curve. So we get an area of 2/3. Again, this one's a little bit, excuse me, a little bit harder because we have to set up a sum that's not regular. In other words, the interval sizes are not all the same size. And again, you can see that from that example that we did earlier when we looked at our number line here. Right? The interval sizes are all different sizes. Okay? And so the intervals are all different sizes, and that's what we're doing here, and that's the more general Riemann sum. Now, we didn't go very completely general because we always pick the right-hand endpoint, but again, you can see our result, though, is 2/3. Okay. Hopefully this gives you a little bit more insight, shows you how, at least in some situations, you can do a problem like this. You can actually repeat this process for any root. This idea would work with some adjustments for a cube root and for other things like that. So you may consider trying, to find the area beneath the cube root of x on the interval 0 to 1. And we'll leave you with that. Again, our area is 2/3. And we'll stop there.